IP addressing. In this section, we'll talk about what IP addresses are, and we'll see how an IP address is actually made up of a host ID and a network ID. We'll talk about what a physical segment is and how important that is, and then we'll talk about address classes, class A, B, and C, also D and E. We'll finish up by talking about the different addressing modes we have, public and private, and then finally we'll talk about acquiring IP addresses. Every single device on the network that uses TCP/IP requires a unique IP address. Now that could be a computer, sometimes they're called hosts, but it doesn't matter if it's a mainframe computer, a mini computer, or a personal computer, it requires a unique IP address on every network interface card that uses TCP/IP. Routers will generally have multiple IP addresses, one for each port or connection they have. Printers will have IP addresses if they use TCP/IP, and any other device that uses TCP/IP will require a unique IP address. Now here's an example of an IP address, 206.77.105.9. Now this address would have to be configured in the TCP/IP software. If you typed it in manually, that would be statically configuring the IP address information. Also, we have servers like DHCP servers that can automatically configure TCP/IP addressing. An IP address is really just a 32-bit binary number, a big long string of zeros and ones. Now, to make it more convenient for us, we divide the 32-bit number into 4 8-bit octets. Then we take those 4 8-bit octets and we convert them to decimal numbers, like we did in binary math. So what I've done is I've taken the binary number listed on the slide here and converted it into the decimal number 192.168.113.19. Each of those numbers equates to a specific binary number. In fact, it's important to note is that if I was to type this IP address into the computer would convert that back into the binary number without regard to any of the octets or the periods. Because to the computer, the IP address is a big long string of binary numbers. Now, as part of our binary math, we looked at if we took an octet, we could convert it to a decimal number. So we know from binary math that any octet could have a decimal value between 0 and 255. That means each of the octets could have any possible number between 0 to 255. Now we're going to see a little bit later with IP addressing that certain numbers are off limits, but potentially each one of those octets could be any number between 0 and 255. Now, an important thing to note, and we'll be talking about this coming up, is the IP address contains both a network ID and a host ID.
Each IP address has two portions, a network ID and a host ID. Now, the network ID is common or shared by all computers on the same physical segment. Now, for instance, in the example here, I have an IP address 192.168.113.201. We're going to say that the network ID is 192.168.113.201. That means all computers on the physical segment would have the network ID in common. They would all start with 192.168.113.201. And then each computer or each host on that physical segment would have a unique host ID. The first host would be number 1, second host number 2, and in this case we're looking at the host number 201. So again, all computers on the same physical segment have a common or shared network ID, in this case 192.168.113.201, and then each host on that physical segment is identified by a unique host ID, number 1, number 2, number 200, number 201. Now, also, each physical segment has a unique network ID. Now, we looked at the first physical segment with a network ID of 192.168.113.201. If we were to go to another physical segment, it would have to have a unique network ID, maybe 192.168.12, but that network ID would then be shared by all computers or all devices on that physical segment. and then each of those devices would have a unique host ID. And then we go to additional physical segments, giving each physical segment a unique network ID, keeping in mind that then those hosts have to be numbered uniquely on those physical segments. Now, the best way to think about this is to think of the network ID in the context of an area code, as in it's shared by all the telephones in an area, and then each telephone has its unique phone number, which is like a host ID. One key piece of terminology we must be familiar with is, what is a physical segment? Now, a physical segment can be thought of a broadcast domain. Now, when we talk about a broadcast domain, we're talking about a portion of the network or all devices that can exchange information using a broadcast packet. Now, if two devices are separated by a repeater, a bridge, or a switch, they are considered in the same broadcast domain because these devices will forward broadcasts. However, if we have a router will not forward broadcast, and they really define our physical segments. So our definition of what is a physical segment, well, it's everything out one port of a router or between two routers, and that's again because a router does not forward a broadcast. Now, this is important because of our IP addressing rules. Remember, all devices on the same physical segment share a common network ID. So that means all devices out one port of a router or between two routers would be on the same physical segment, and therefore they would have the very same network ID. Now, of course, they'll have a unique host ID to give them a unique IP address, but they all share a common network ID. Also, each physical segment has a unique network ID. So if we have a router with 3 different ports, that would give us 3 physical segments, and each physical segment would have a unique network ID, keeping in mind that all devices on each of those physical segments would share the common network ID for that physical segment. There are a couple of very important IP addressing rules. Now, each device or each host needs at least one unique IP address. Actually, a host needs a unique IP address for each connection to the network. So if a host, for instance, or a computer had 3 different network interface cards, each network interface card would require a unique IP address. Also, all devices on the same physical segment share a common network ID or network portion of their IP address. Now, they will have a unique host ID, but again, all devices on a physical segment share a common network ID as specified by the subnet mask. Also, if your network has multiple physical segments, each physical segment would have a unique network ID, and of course, all computers on each physical segment share that physical segment's network ID.
When IP addressing was first set up, it was based upon a classical naming scheme. A network could be set up with a Class A address, a Class B address, or a Class C address. Now, the address class specifies which octets of the IP address are the network ID and which are the host ID. The address class also specifies the size of the network, or shall we say, the number of hosts that the network could support. As I mentioned before, the address class specifies which portion of the IP address is the network ID and which portion is the host ID. A Class A address, the first octet is the network ID, the last 3 octets are the host ID. Now, a Class B address, the first 2 octets are the network ID, the last 2 octets are the host ID. Now, Class C, first 3 octets are the network ID, last octet is the host ID. And in the case of Class D and E, we haven't mentioned those before, those are special addresses and not available to number our networks with. As I stated before, the IP specification states that for a Class A address, the first octet is the network ID and the last 3 octets are the host ID. Now, to define that further in binary, a Class A address is any address that starts with a 0 in the first bit of the first octet. So the first possible Class A network address, now in binary, would be 7 zeros, a 1, and then the rest zeros. And when we do a decimal conversion, the first Class A network address available would be 1.0.0.0. Now, the last Class A network address available would be, now again, a Class A network address has to start with a 0 in the first bit of the first octet, but the last one possible would be 0 with all 1s in the first octet. Now, if we do a conversion to decimal there, we see that that address is, in decimal, 127,000. Now we're going to see that that 127 address is a special address called the loopback address. Now the loopback address is built into every TCP/IP computer for testing and diagnostic purposes. So a Class A network could be any network starting with the decimal number of 1 and going all the way to 127. When looking at the possible network IDs for Class A networks, we see that the first decimal number network would be 1.0.0.0. The second one 2.0.0.0, 3.0.0, and so forth until you got up to the last Class A network, 127.0.0.0. Now remember, that is a special loopback address that cannot be assigned to any network. Now, the Class A network, the first octet is a network ID, and then the second, third, and fourth octets, again, are the host IDs. Now, if we were assigned a Class A network address like 33.0.0.0, all computers in our network would start with 33, and then the administrators would then assign the host IDs to the individual computers. Calculating the number of possible Class A networks or possible Class A network IDs is easy, because the first one we could use is 1.0.0.0, and we could use all of them all the way up to 126.0.0.0. Now remember, 127.0.0.0 is technically a Class A address, but it is reserved for loopback or diagnostic purposes. Now calculating the number of host IDs on each Class A address network is also easy. Now remember, according to the specification, the last 3 octets are reserved for host IDs. Now remember, each octet gives you a possibility of 256 addresses, or in this case host IDs. And so to determine the total number of host IDs, we take the 3 octets, knowing that each one has a capability of supporting up to 256 addresses, and multiply them. 256 times 256 times 256, and that gives us over 16 million possible addresses. Now keeping in mind that whenever we calculate the number of addresses, we always subtract 2 from that, because the address, okay, any host address, cannot be all zeros or all ones. So for instance, if our network address was 33.0.0.0, we could not use the host ID 33.0.0.0 because that indicates that is the network address, and we could not use the host address of 33.255.255.255 because that's reserved for broadcasts. Determining the actual host IDs available to a Class A network can be a bit tricky. Now in this example, we've been assigned the Class A address 33.0.0.0. All computers or all devices on our network would start out with 33.0.0.0. That's our network address. And then we would have the last 3 octets to start assigning host IDs. Now remember, in this case, a Class A address gives us over 16 million different host IDs. Now the first host ID we could use would be 33.0.0.1, and then we would increment that, the 1, the 2, the 3, all the way up to 255. Then the next possible address after that would be the 33.0.1.0, and then that would increment all the way up to 33.0.1.255. Now each one of those numbering sets has 255 addresses. Once we got up to 33.0.255.0, that would give us 65,000 addresses, and then we would start the incrementing over. And then each time we incremented the second octet, that would give us another approximately 65,000 addresses. And by the time we got done, now again, we started at 33.0.0.1, and the last possible address would be 33.255.255.254, the 255 being thrown out because it's a broadcast. That would give us our 16.7 million addresses. Remember that the IP specification states that a Class B network has the first 2 octets as the network ID and the last 2 octets as the host ID. The specification further states that a Class B address is any address that starts with a binary 10 in the first 2 bits of the first octet. Now the first Class B address would be listed there in binary 1 with 7 zeros. Now, when you convert that to decimal, that's 128.0.0.0. So in that case, the network ID would be, because it's class B, 128.0, and then the host IDs would be starting at 0.0. Now, the last possible class B network address would be 191.255.0.0, because 191 is the last number in decimal that starts with a 10 as the first 2 bits of the first octet. So that's the last class B, and in that case the network ID again would be 191.255, and then the host ID would be the last 2 octets. Remember, according to the IP specification, a Class B network is a network in which the first 2 octets are the network ID and the last 2 octets are the host ID. Now, a Class B network, the first one would start with 128.0 as a network ID, and then the last 2 octets would be available for host IDs. The next available Class B network would be 128.1, then 128.2, 128.3, all the way up to 128.255. Then we start over at 129.0, 129.1, 129.2, all the way to 129.255, and on and on and on until we got up to the last possible Class B address, 191.255.0.0. And that would give us quite a number of Class B addresses. Now, if your organization was assigned a Class B address like 153.11.0.0, all devices, all hosts on your network would start with 153.11, and then you as the administrator would assign the host IDs in the 3rd and 4th octets. Calculating the possible number of Class B networks is straightforward. Now remember, according to the IP specification, in Class B networks, the first 2 octets are the network IDs and the last 2 octets are the host IDs. Now the first octet could be any number from 128 to 191, according to the IP specification. Now remember, 1 through 127 in the first octet is associated with Class A addresses. So in the first octet we have 64 possible network IDs. Now the second octet is entirely dedicated to network IDs. So in the second octet we have 256 possible network IDs. So the total number of B network IDs that are available, it would be 64 times 256, or over 16,000 possible Class B addresses. Now, the last 2 octets are dedicated to be the host IDs, and in each of those octets we have 256 possible host IDs. So the number of hosts would be 256 times 256. That's the 65,536 possible host IDs, but remember, we throw out the all ones and the all zeros to come to the answer of the number of host IDs in a Class B network of 65,534. Assigning the host IDs associated with a Class B address is straightforward. Now, in my example here, I've been assigned the Class B address, network address, 153.11.0.0. That means my network ID is 153.11, and this would be shared or be assigned to all devices or hosts on my network. And then I, the administrator, would then assign the host ID starting with 153.11.0.1. Next one would be 0.2, 0.3, all the way up to 0.255. Then I would increment the 3rd octet to 1.0, 1.1, all the way up to 1.255. And I would keep incrementing the 3rd octet. Each one of those increments would give me a possible additional 256 addresses until I got to the very last host, 153.11.255.254. Now the 255 we'd throw out because that's the broadcast address. Now that would give me a total addresses of 65,534 addresses with my Class B network address. Remember that the IP specification states that a Class C network has the first 3 octets as the network ID and the last 3 octets as the host ID. A Class A address also is defined as any address that starts with a 110 in the first 3 bits of the first octet. Now again, calculating out the binary into the decimal, we see that the first possible Class C address would be 192.0.0. That would be the network ID of the first Class C network. And the last possible Class C network address would be 223.255.255. According to the IP specification, a Class C network address has the first 3 octets designated as the network ID. So the first possible Class C network we'd have would be 192.0.0. The second network ID we would have would be 192.0.1, next one 192.0.2, all the way up to 192.0.255. Then we'd increment the second octet for additional Class C networks, 192.1.0, and on, all the way till we got to 233.255.255. That would be the last possible Class C address, network address according to the specification. Now, as you can see, there's a great many Class C network addresses. Now, if we were assigned a Class C network address for a network like 201.11.206.0, all computers on our network would share the first 3 octets as our assigned network ID, and then as the administrator, we'd have the last octet to hand out host IDs. To determine the possible number of Class C networks, we see that the first octet could have any value between 192 and 223 in decimal. Now remember, the numbers before 192 are either Class A or Class B addresses. So the first octet has 31 possible IDs, and then we have the entire second and third octet dedicated to network addresses. So in both of those cases, we have 256 possible IDs. So the total number of Class C network IDs is 32 times 256 times 256, which is about 2 million different possible Class C networks. Determining the number of host IDs is really quite straightforward because we have a single octet dedicated to host IDs, which would give us 256 possible addresses minus 2. Can't use the 0 or 255 because they're reserved. Numbering the hosts on a Class C network is really easy. We start out with, for instance, our assigned Class C address at 201.11.206. Now, all devices in our network would start with those very same numbers, 201.11.206, because that's our network ID. And then as administrator, we would start numbering our hosts 1, 2, 3, all the way up to 254. There are also Class D and E addresses. Now, we can't use these addresses to number our TCP/IP hosts. They're used for special purposes. Now, Class D addresses are used by multicast applications. These are shared addresses that are used by multiple numbers of hosts at the same time to listen to multicast communications. Now, these addresses start at 224.0.0.0 and go all the way up to 239.255.255.254. Now, Class C addresses 240 and above, they're experimental, and again, they're off limits.
Address classes are important because they specify which portion of the IP address is the network ID and which portion of the IP address is the host ID. Now, in a Class A network, the specification says that the first octet is the network ID and the last 3 octets is the host ID. Now, the way you can tell a Class A address is because the first octet is a number between 1 and 127, and any IP address in which the first octet is between 1 and 127, we know that it's a Class A address. And then we know that the first octet is a network ID and the last 3 octets are the host ID. Class B addresses start with any number in the first octet, any decimal number in the first octet from 128 to 191. If we see an IP address that starts in that number range, we know it's a Class B address. We know that the first 2 octets are the network address and the last 2 octets are the host address. Likewise, if the first octet of an IP address is a number between 192 and 223, we know that that's a Class C address, and if we know it's a Class C address, we know that the first 3 octets are the network ID and the last octet is the host ID. Our address class summary lists the different address classes and the number of possible network IDs in each address class and the number of host IDs that each network ID provides. Now, there are 126 possible Class A network IDs. Now, each Class A network ID can support over 16 million different host IDs. Now, there are over 16,000 different Class B network IDs, and each Class B network IDs can support over 65,000 host IDs. Class C networks, there are a possible of over 2 million different network IDs, and each network ID, each Class C network ID, supports 254 different hosts.
An IP address is really just a 32-bit binary number, a big long string of zeros and ones. Now, to make it more convenient for us, we divide the 32-bit number into 4 8-bit octets. Then we take those 4 8-bit octets and we convert them to decimal numbers, like we did in binary math. So what I've done is I've taken the binary number listed on the slide here and converted it into the decimal number 192.168.113.19. Each of those numbers equates to a specific binary number. In fact, it's important to note is that if I was to type this IP address into the computer would convert that back into the binary number without regard to any of the octets or the periods. Because to the computer, the IP address is a big long string of binary numbers. Now, as part of our binary math, we looked at if we took an octet, we could convert it to a decimal number. So we know from binary math that any octet could have a decimal value between 0 and 255. That means each of the octets could have any possible number between 0 to 255. Now we're going to see a little bit later with IP addressing that certain numbers are off limits, but potentially each one of those octets could be any number between 0 and 255. Now, an important thing to note, and we'll be talking about this coming up, is the IP address contains both a network ID and a host ID.
There are a couple of very important IP addressing rules. Now, each device or each host needs at least one unique IP address. Actually, a host needs a unique IP address for each connection to the network. So if a host, for instance, or a computer had 3 different network interface cards, each network interface card would require a unique IP address. Also, all devices on the same physical segment share a common network ID or network portion of their IP address. Now, they will have a unique host ID, but again, all devices on a physical segment share a common network ID as specified by the subnet mask. Also, if your network has multiple physical segments, each physical segment would have a unique network ID, and of course, all computers on each physical segment share that physical segment's network ID. Address classes are important because they specify which portion of the IP address is the network ID and which portion of the IP address is the host ID. Now, in a Class A network, the specification says that the first octet is the network ID and the last 3 octets is the host ID. Now, the way you can tell a Class A address is because the first octet is a number between 1 and 127, and any IP address in which the first octet is between 1 and 127, we know that it's a Class A address. And then we know that the first octet is a network ID and the last 3 octets are the host ID. Class B addresses start with any number in the first octet, any decimal number in the first octet, from 128 to 191. If we see an IP address that starts in that number range, we know it's a Class B address. We know that the first 2 octets are the network address and the last 2 octets are the host address. Likewise, if the first octet of an IP address is a number between 192 and 223, we know that that's a Class C address, and if we know it's a Class C address, we know that the first 3 octets are the network ID and the last octet is the host ID.